There are lots of stuff that use springs every day, like suspension, trampolines, toys, and even microwaves. The purpose of investigating Hooke's law is to discover the properties of springs in different applications and how they are influenced by weight and force. The aim of the investigation is to determine how spring length influences the spring constant. The hypothesis is the largest spring in length will have the greatest spring constant. The diagram shown outlines some of the materials needed. Here is the list of the materials needed. A scale measuring grams or kilograms. A ruler measuring centimeters. Different lengths of springs. A small mass. A retort stand. And a flat surface or table. A weight holder, weights, and a clamp. Number 1. Attach the spring to a retort stand and clamp. Number 2. Using a ruler, measure in centimeters the equilibrium position of each spring. Number 3. Weigh a small mass on a scale, measuring grams or kilograms, and record its mass. Number 4. Attach the small mass to the spring and measure the displacement. Or, measure the length of spring, then subtract the equilibrium length. 5. Calculate the gravitational force exerted by the mass on the spring using F equals mg, or force equals mass times gravity, with gravity being 9.81 meters per second squared. Number 6. Last step, using Hooke's law to calculate spring constant for each spring. F equals minus kx. X is displacement. Here is the results table. Here is the results graph. It shows the relationship between spring constant and spring length. The trends of the graph and the table are as follows. The results that were obtained were consistent and supported my hypothesis. All of the springs tested were of similar lengths and thus had similar results. Spring 1 was 13.5 centimeters and had a spring constant of 1.681 newtons. Spring 2 was 15 centimeters and had a constant of 2.943 newtons. The last spring tested was 2 centimeters larger than spring 2 and thus had a larger constant of 3.924 newtons. The results showed that as length increased, spring constant increased. This trend was supposed to be linear, and spring constant and length are proportional to each other, and this supports my hypothesis. There was no unusual results, as the springs tested were of same diameter and type, none of which were permanently deformed. As the lengths of the springs differed, spring 1 was 13.5 centimeters, while the other two springs were 2 centimeters apart. This was a minor inconsistency. The evidence showed in the graphs and the tables are also supported by my hypothesis, as they abided by Hooke's law. Conclusion. Springs with larger spring constants were bigger in length than those with smaller spring constants, proving my hypothesis right. Any spring with the same diameter and type should abide by Hooke's law, as investigated in the experiment. Validity and reliability. This experiment possesses a high validity as it effectively investigates Hooke's law using tools and strategies that successfully and accurately measure the length and constant of the given spring. The materials used are appropriate to the experiment. The controlled variables were also constant in every test, and only the length of the springs changed. All of these factors ensure that the investigation is of the highest validity. However, only 3 different length springs were tested in the process, and the process was repeated twice. As a result of the low number of springs and the low repeatability, this investigation encompasses a low reliability. Improvements. One improvement of the experiment is that the repeatability should be increased. Repeatability is an important factor of any experiment and influences the reliability and accuracy. If the repeatability was increased, the reliability would improve, thus improving the overall quality of the experiment. Another important improvement to the experiment is the amount of springs tested. This is important because the experiment would have been more reliable and accurate, also improving the overall quality of the experiment.